This is day 26 of the 30-day Leetcode challenge. Let's start loading it. Okay. Hit the like button, hit the subscribe button. Let me know how you feel about this problem. How did you do it? Did you solve it okay? I don't know. But we'll see how I solve it too. Anyway, longest common subsequence. Given two strings, text 1, text 2, return the length of the longest common subsequence. The subsequence of a string is a string. Okay, yeah, it's deleted. I mean, this is a very common definition, so I feel like that's okay. If there's no common subsequence, return 0. And n is 1,000. And so, okay. So I would say this is a very, oops, I clicked on hit back. No, okay. So this is a very standard dynamic program problem, so definitely practice it. There's really not much. So the idea, so the state behind this dynamic program problem is x, y, where x is how many letters you processed on text 1, and y is the number of letters you process on text 2. So this is very standard. I urge you to practice it. You're going to see me code right now. I think I'm going to try, for this problem, because it is a very standard problem, I'm going to try to, I'm going to go step by step. How do you convert from a top-down dynamic programming problem or top-down recursion / memorization problem, and then convert that to a bottoms-up dynamic programming problem or solution. And then from that bottoms up, try to show you, ways to make that the space complexity a little bit better. So I'm going to do that. And yeah, go with me, and then let me know how you, leave in the comments, let me know how you feel and all that stuff. And from that, so usually, if you're a regular watcher of the stream, and I urge you to subscribe so you could be a regular viewer. So I would do something like, so what I would do, if I'm on a competition, I would do something like from func tools, import LRU cache, and then just do the memorization that way. But this time, just for educational purposes, I'm going to write it out more explicitly. I think one thing that I have noticed, for better or for worse, is that I've seen a lot of people have been using LRU cache as a way to solve problems without really analyzing the complexity or the space complexity and so forth. So I'm going to try to be really explicit about this. And yeah, and step with me. And if you already know how to solve this, then you probably won't be watching this video because this is a very standard problem for, which is unfortunate for Leetcode maybe, but I don't know. But it's a good practice to learn and good practice to practice on. Yeah. So now I'm just going to start with a recursive function. Let's just call this, I mean, naming is tough, but I'm just going to call this longest. And then let's call it index 1, index 2. And here, index 1 refers to the number of, refers to the index of text 1 that we're currently processing. Index 2, ... text 2. Same thing, right? Okay, and then now, depending on how you want to feel about it, sometimes I write the base case first, sometimes I write the transitions first. Yeah, so right now I'm going to try to think about the base case first. And the base case, what is the base case? Well, if index 1 is equal to, okay, let's also declare this n is equal to length of text 1. Actually, let's name this a little bit, n1 and n2. I was going to use n and m, but maybe that's not super clear. I mean, it doesn't really matter either way, right? But for now, we have all the 1 suffix and all the 2 suffix. Cool. So now if this is equals to 1, that means we processed all the letters from the first string from text 1, right? So what does that mean? That means the answer is going to be 0, right? Because no matter what you do on the second string, you're not getting an answer because you have no more strings from the first string, no more characters from the first string. And then similarly for index 2, I think. Let me know if you have questions with that. So yeah, so then now, those are your base cases, and that's pretty much, I think that's it. And then now for your transitions, what are your transitions, right? Well, your index 1, index 2 of the 2 strings. So let's just say best is the current longest string. So let's set that to 0 because, well, you can't get negative. and those are like that's just your set no default case. And then now let's break down the case. Okay, if the text 1 of index 1 is equal to text 2 of index 2, that means currently the beginning of the two strings, if they're equal, then wow, then you could pop them and then you could put them on as as part of the longest common string, right? So then now the current the I wouldn't say current best maybe, or the current result for matching. So let's just call it matching score. The score you get from with their match is equal to the longest of index plus 1, index 1 plus 1 and index 2 plus 1, because we move both of those indexes forward. And then we add 1 because we match one character, so that's 1 more to the score, right? And then now we're going to do best is equal to max or best matching score. And then let's say, but we don't know if that's the best score, right? So we just, given this case, this is one case that we're considering. What's another case you're considering? Well, so that means that, or let's assume that they don't match. Even though we could even assume that match, it doesn't really matter. But let's say we don't want to match. So now there's a transition, right? Well, when we don't want to match it, then we can either throw away the first character or the index 1 from the first string, or we could throw away the index 2 from the second string, right? Because we're like, okay, we chop off the beginning of it and we don't use it, and then there are subproblems, and then see how good that goes, right? So that's what we're going to try to do. So now we can just write score is equal to longest index 1 plus 1 index 2, and then best is equal to max of score. And I don't usually write it this way, but this is for a little bit for clarity. And then now, so that's pretty much what we have, right? So what's the complexity of this? Well, right now, we don't do memorization, right? So so this is going to be exponential because at every point you're branching out to up to 3 places, roughly speaking. So it's going to be like 3 to the n or something like that, or exponential. So what we want to do now is to do something what we call memorization. One thing to notice from this function and is that, well, index 1, what are the bounds for index 1, right? Well, index 1 is always going to be between 0 and n1, and index 2 is going to be between 0 and n2, right? So what does that mean? Well, that means, and because that, if you count them as dimensions, that means that there are n1 times n2 possible place. Like, so if you look at all the possibility for inputs into this function, there's, well, n1 could be, there are n1 possibilities for index 1 and n2 possibilities for n2, index 2. So then now you can just multiply them together because they're independent, and you get n1 times n2 for the number of states that happen here. So what is the complex? So that means that we can store it because n1 is 1,000 and n2 is 1,000. So n1 times n2 is only about 1,000,000. So let's put it here. So I would write normally my normal contest code, or even my normal code might be a little bit different. But right now I'm just trying to be as explicit as possible. So let's create a Boolean array for a scene. And this is in Python, so the syntax is a little bit weird, but so one, I think actually the other way, but and 2 for and the syntax is a little weird, but basically it just creates an n1 by n2 matrix of booleans, and then we're going to try to do the same, but for the best score. Okay, right, and then now we can do something like, okay, assuming that this doesn't reach n1 or n2, we could do something like, if we've always seen index 1, index 2, then let's return dp of index 1, index 2. That's where we put it. And then otherwise we've already solved these problems. So let's set this to scene index 1's index 2 is equal to true, and then dp index 1 index 2 is equal to the best score, right? So that's kind of the memorization. And so what is the complexity of this function? Well, as we said, the number of possible inputs, which sometimes you listen to it as referred to the number of possible states, will be n1 times n2 or n times m, depending on how you want to define your things. And because during each state, you do a constant amount of work, which is 3 at this point, making references to other states. Well, that's going to be constant time each. So the entire running time will be n1 times n2, or maybe n times m, depending on how you want to define it. And then now we just have to kick it off, which is return longest of 0, 0. And there we go. Let's give it a twirl. Let's put in some more test cases, at least from the ones from the inputs that they tell you, and then maybe just some really big cases. That's not even that big. What is 1,000? Okay. Okay. It's 10, 20, 40, 50, 60, 70, 80, 90, 100, and then 1, 2. Okay, so that's 1,000. I hope, close enough. And then we have 1,000 by 1,000. Let's see. Just to kind of see the running time. And it's a little slow, but that's okay. As long as it is good enough. Let's submit. Yeah, so that's one of the ways to solve this is with dynamic programming or top-down memorization. I hope that is a good enough explanation so far. If not, you might have to kind of, there are a lot of good videos on memorization and how to kind of get to it. But this is how I would attack this as a general memorization problem. And now, as I promised, let's try to do this with for loop, right? Or with what we call bottom-up dynamic programming. So now we have this function, and we can kind of figure, and we have these set up. That's okay. So the idea behind bottom-up dynamic programming is that by the time you order your processing in a way such that by the time you process a state or a cell, a state or a cell, all the previous calculation for it has already been done. Where here, it's almost like, okay, you need the current situation that depends on these other states. So yeah. And also, the thing with this problem, one thing to also note, now that I notice it, is that this problem is symmetric. And what that means is that you go forward and backwards equally. You could also imagine an equivalent problem where you count down from n1 to index 1, n1 to 0 and n2 to 0. And it'll be equivalent because this is symmetric. Not all dynamic programming problems are symmetric in that way, so be careful. That's the one other tip. But from that, let's erase this. And because now that we know that we're going to do it in the order that makes sense, where all the work has already been done, we could get rid of this. And now let's set up the base case, right? Well, what's the base case? So the base case is similar to what we had before, but now let's so before, if you notice how we structure it, we never get to the case where n1 and n2 gets hit. So now, because you might, at least it makes the if statement easier to use, we're going to just add 1 to this so that we have better set no values. That's mostly it for the setup, because the base case are all just zeros, and you're constructing the best score as you kind of build, right? So now we can just do for x is in range of n1 plus 1. Yeah, for y is in range of n2 plus 1. So now we actually, it's not a one-to-one mapping, and what I said about the symmetry actually makes it slightly easier. Because now, so before we have a function that, I forget what I think I just call it longest. Longest index 1, index 2, right? So now we actually want to change it slightly differently. We want to say dp of index 1, index 2 is the best score, for, let's see, text 1 from 0 to, I'm writing explicit, I know that, from inclusive. Yeah. Or disinclusive, sorry. Yeah, so it's from disinclusive and disinclusive. So, so yeah, so from that we can, everything else is very similar, which is that if text1 of x is equal to text2 of y, then dp of x y is equal to, should be max of dp of this plus 1 and just itself, I suppose. And that's pretty much it, really. Well, not really, sorry. Because that's the equal case. But as you recall, we had two other cases where we were like, okay, let's take the best from either one. So otherwise, dpx of y is equal to max of dpx minus 1 y, and y. I might have it off by one. Hang on. And I think here we were very explicit about x and y is equal to, sorry, this x and y is, yeah, so we actually have to start by 1 because otherwise you get zeros, and this is x minus 1, y minus 1 for that. And that's pretty much it. And what is our best score, right? Best is 0 in the beginning. And let's look, the best score can end anywhere, so let's set the best score as equal to max of best of dp of x of y. Also, by we, I mean me, forgot to write this part. And then now we just have to return best. Let's run it real quick. Yeah, so that's kind of pretty much it. Yeah, accept it again. We should still just for science. I'm going to take a look at this seconds. So now that one was 9. So that one was 1 second. Don't know how to see my other submissions. Okay, well, maybe that's okay. I just wanted to maybe do a comparison, but that's okay. But yeah, so as you can see, we retain all three of our states. Our base case is implicit because our 0 states will be 0, which we set here as the default state. And I urge you to kind of, feel free to go back and forth in this video between the two solutions and see how they translate. It's a little bit tricky, and it will take experience, especially if you want to get it without, like, the first try without doing all these like back and forth. It's going to be a little bit tricky, but do practice. And with practice, you're able to kind of, I think the tricky case is about the base cases sometimes, where it's a little bit weird. So what are the trade-offs, right? So the thing with top-down is that in some problems, not all the states will be visited. And in that case, it'll be, and in that case, where all the states are not visited, well, it'll be faster because you're not visiting all the states. The benefit of the bottom up is, well, one is it's lower, what should we call it, lower costs in general. I mean, it's not like O of n costs or whatever. It's just lower costs because you don't have to worry about stack overflows. You don't have to worry about the stack costs in general. Everything, as you can see, is a couple of for loops, and those are really cheap operations, even if they have the same overall complexity. And then the second one, which we will do right now, is that there are more opportunities to optimize the space efficiency. Okay, and this is what we're going to do right now. And there are actually a couple of ways to do this. I'm going to do it the more explicit way because usually there are a couple of tricks even in terms of programming to make it easier. But I want to go for the way that is the more illustrative. Or like easiest to understand. Put it that way. So now, one thing to notice is that if you look at all these transitions, what can we say about these transitions, right? Well, if you look at the x component of all these dimensions, you only see x minus 1, or x, I guess, but x or x minus 1, right? And what does that mean? That means that, let's say you have a matrix. Yeah, you have some matrix of some number, and we're populating the whole thing. I don't know. Like, this is really made up, right? So don't worry about it that much. So you have like something like that, say maybe, and then and then you have duplicate of it, not duplicate, but you just have more rows, and something like this, right? But to fill out the next row, what happens here? Well, you only need to look at this row, right? So we actually never look at the rows previous to that. So what does that mean? That means we can actually throw it away. And when you throw it away, what does that really mean in terms of space? Well, when you throw away those space, that means you can actually reuse these cells or reuse the storage. And instead of allocating the entire matrix, which is n times m or n1 times n2, you only need all of n1 or all of n2, depending on how you want to structure it, but effectively the same in the big O. And you could choose, obviously, and you could just swap the strings if you don't like which one is the dominant one. So that's kind of the strategy. And then I'm going to be a little bit explicit, and then let's create a previous array. And then now let's look at, oops, no, I don't even know how to go. Something like that, right? And there are tricks about it, obviously, but I'm going to try to be as explicit as possible, which is that, okay, well, in this way, and here, the transformation is actually pretty straightforward, right? Well, what is previous is just equal to dp sub x minus 1, and then now is equal to dp sub x, right? So all we have to do is just copy and search and replace, essentially. So this prefix is now, right? So as you kind of see from this other comment. So now, this is previous, and this is now. Oops. And that's roughly pretty much it. There's only one more caveat or one more thing you have to do is that after every iteration we have to change some stuff, right? So now after you loop through all this, we have to set previous as so the current now is going to be next iteration's previous. So that's what we're going to do. So now we write for y and range. Let's do len of previous. And then now previous sub y is equal to now sub y. And then now sub y, we could set it to 0. It doesn't really matter. It's just a base case. Actually, yeah, no, it should be 0. Though, if you look at this is the general way you would maybe clear it. But you can also notice that okay, well, maybe as an exercise for the viewers at home, specific to this problem, there's actually a few very micro optimizations. It's not a big deal, but check it out. But anyway, so that's how I would structure it. Let's run the code real quick. Whoops. Oh. Oh, I just, maybe I have a typo, hang on. Oh, whoops. I just initialized wrong. I still initialized the matrix, but should be, they're both array of length n2. It's a minor typo. Yeah, so same answer. I mean, because we only changed the code in a very minor way. So yeah, let's submit it. I mean, other than typos, it should be mostly okay. And yeah, and let's take a quick look to see the performance. Yeah, so it's a little bit faster. I actually didn't remember what the memory usage is, but though in this case, from a million to 1,000 is probably not a big deal. But that's how you would generally do it, especially when you're faced with a problem where, well, you can't fit the n square in memory. If n is any bigger, you cannot fit in the memory. Or if you have even more dimensions, these are the ways that I would optimize this problem. Yeah. So now let's look at the three solutions that we did. So the first one was the top-down memorization. There's a lot about stack space and stuff like that, so that's why it both takes more memory. I mean, it takes about the same memory plus stack space and stuff like that, because it could be up to n1 plus n2 stack space, and it's just more overhead. Overhead was the word I was looking for earlier. So that's the top-down. And then we optimized it a little bit by using the bottoms-up dynamic programming. And as you can see, it does perform a little bit better because we use all the states anyway, and because there's less overhead. And then now you can see that by doing the memory optimization, well, one is because we spend less time allocating that memory, the running time is faster too. But then the second time is obviously the memory also goes faster, so the memory is much lower usage. So yeah, so that's kind of the difference between the three approaches. And hope everyone did well. Anyway, so I think for this problem we went over. Yeah, we went over all the ways I would solve this problem. We went from, as a review, if you want to go back and rewatch this, because I think this is very fundamental, is we did it with top-down dynamic programming, memorization. We translated a little bit with that understanding to bottom-up dynamic programming, and then we did the space optimization that is very common from time to time anyway. So yeah, so that's all I have for this problem. Hope you enjoyed this explanation. Hit the like button, hit the subscribe button, and yeah, we'll see you soon. Bye bye.